Now we are going to another result. So that is the existence of primitive root mod p for all prime p. Existence of primitive root mod p. Existence of primitive root mod p for all prime p. So before going to that one, first we are going to a lemma. So the lemma is if a and m are relatively prime. If a and m are relatively prime and f is exponential a mod m, that is x be the least positive integer such that a to the power f congruence to 1 mod e. Then exponential of a to the power k mod m. Then exponential of a to the power k mod m is same as exponential of a mod m divided by GCD of k and f. Now, in particular, if GCD of k and f are 1, means if k and f are relatively prime, then exponential of a to the power k mod m is nothing but exponential of a mod m. So this is an important lemma. So that's very interesting. How to prove this one? A and m are relatively prime. And what is f? F be the least positive integer such that a to the power f congruence to 1 mod m. Now, let x equals exponential a to the power k mod m. This means it is if f is exponential a mod m, then a to the power f congruence to 1 mod m. So here a to the power k all to the power x congruence to 1 mod m, where x be the least positive integer. X be the least positive integer such that a to the power k all to the power x congruence to 1 mod m. That means a to the power kx congruence to 1 mod m. Okay, but we know that if a to the power k congruence to 1 mod m, this should imply k congruence to 0 mod f. This is a well-known result. If a to the power k congruence to a to the power h mod m, then h congruence to f mod e. So k congruence to h mod f. So this is a special case of that result. We know that if a to the power k congruence to a to the power h mod m and f be the least positive integer such that a to the power f congruence to 1 mod m means f is exponential a mod m, then this implies k congruence to h mod f, where f be the least positive integer with a to the power f congruence to 1 mod m, or it is the exponential a mod m. So instead of when h equals 1, so 0, when h equals 0, it is 1, when h equals 0, a to the power 0 is 1, so here k congruence to 0 mod f. So this is the special case of this result. Yes, we already proved this result. If a to the power k congruence to 1 mod m, that should imply k congruence to 0 mod f. So in the light of that argument, if a to the power kx congruence to 1 mod m and f is exponential a mod m, then we know that kx congruence to 0 mod f. It is kx congruence to 0 mod f, where x be the least positive integer. Why? Because of the choice of x. Agreed. And we have by the cancellation law of congruency, if AC congruence to BC mod m, then this should imply A congruence to B mod m by d. What is d? D is the GCD of m and c. This is the cancellation law regarding the congruence relations. This is the cancellation law regarding congruence relations. That is, if AC congruence to BC mod m, this should imply A congruence to B mod m by d. What is d? D is nothing but the GCD of of this m and c. So here, when kx congruence to 0 mod f, and suppose d be the GCD of k and f, if d be the GCD of k and f, then by the cancellation loop you can clearly implies, or this result, this congruence relation implies x congruence to 0 mod f by d. Okay, why? Because of the cancellation. If d is the GCD of k and f, then by the cancellation law of congruence relation, we know that x is congruence to 0 mod f by d. That means the smallest positive solution of the congruence, this is the smallest positive solution of the congruence, x congruence to 0 mod f by d is nothing but f by d. Okay, the smallest positive solution of the congruence, x congruence to 0 mod f by d is nothing but f by d. But what is f? That is so equals f by d. But what is f? F is the exponential of a mod m, that equals exponential a mod m by what is d? D is GCD of k and f. So finally exponential a to the power k mod m is nothing but exponential of a mod m by GCD of k and f, where f be the exponential of a mod m. Clear? So this is clear. This congruence relation clearly implies the smallest positive solution of this congruence relation, x congruence to 0 mod f by d is nothing but f by d, according to our choice. So clearly this f is nothing but exponential of a mod m, and d is nothing but k, GCD of k and f. So finally exponential of a to the power k mod m is nothing but exponential of a mod m by k, GCD of k and f itself. Enough.